And please keep asking questions as we go. I'm going to focus now on this heavy quark spectroscopy. So by that, I mean charm and bottom flavored hadrons. They're not the primary thing we do at JLab, but they are some of the most exciting results that have come out of the field of hadron spectroscopy in the last years, 15 years. So I want to tell you about some of those aspects, and we'll go back and forth between this and the theory and things that we talked about in the first lecture. So we've hopefully I've convinced you that we can study QCD through hadron spectroscopy. When we look at the spectrum of hadrons, the pattern we observe there tells us something about the quark and gluon configurations of these states. Today, or the second session, I'll tell you about some conventional charmonium, so these charm anti-charm systems, and these XYZ states. So again, the goal or the strategy is to look for interesting bumps in the spectrum, look for unique distributions in the decay, and we want to measure for the traditional spectroscopy the mass and the widths of these states and look for patterns in the masses and widths that we see. And so I want to tell you a little bit about those masses and widths and have you do a quick exercise on that to get us going in the second half. So what is the mass and width? We're thinking about if we measure some spectrum, so I'm experimentalist, I collect a bunch of data on this decay of a B meson. I look at all the times that it decays to a J psi and 2 pions, and I just fill a histogram. I increment it for the mass of that observation over and over again. And we see there's this big enhancement here. And so I want to know both what the location of that enhancement is and what the width of that enhancement is to tell me about the nature of the particle, what its mass and width are. And so we do that using a particular kind of function, which is called a Breit-Wigner. So this will be another point for you to get out your laptops and join in with the exercise. The total width of the particle is, as we were looking in the particle data group entries, the sum of all of the partial widths for the individual ways that this hadron can decay. So that that fraction of the decay to a particular kind of set of particles is this gamma I. And the total width is some property of the particle, how broad it is. And it has to do with the lifetime of the particle, inversely related to the lifetime of the particle. So broad particles are have small lifetimes. So what can we actually measure in the experiment? This gets to the question before the break. We can try to measure the intensity of the observed events as a function of mass, and we need a model for that. And the model that we use is this thing called a complex valued Breit-Wigner. There are more complex models, many more complex models, but this is a rather simple one that we'll talk about. And we'll get to play with it with an exercise where this M0 is the parameter that describes the mass, the center of that peak, and gamma is the width. It turns out it's complex valued because all the things that we measure experimentally here actually happen in a complex energy plane. What we actually measure is just along the real axis of that plane, but we do need to model it in terms of a complex quantum mechanical amplitude, and that's what this A describes. So what I'd like for you to do is to try to open this file, which I hope is accessible. And if it's not, you may need to open it in Chrome or something. It's a Python workbook that has, oh boy, switch to Chrome. Let's say yes. Yeah, be accessible. Oh, we don't have Chrome. It's a Google Collaboratory file. So if you have Google Chrome, it should open automatically there. But if not, I may have to pull it up on my Zoom connection. Is anybody else able to open it in Chrome? Is it
anything that can open in Jupyter? Anything that opens Jupyter is okay.
Anything that opens Jupyter is okay? 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 Anything that opens Jup
Yeah, I have it running in VS Code, which is fine.
Okay,
I was able to open it in Firefox.
sorry,
I was able to open it in Firefox.
Firefox opened it too, okay. Let me just connect with a Zoom connection and I can share it from my laptop. Yes. Okay.
I was
On slide number 33.
I had a button that said like.
We have Slack on there.
We'll open Google Collapse up.
Yeah, for me.
Here, let me download this. Just open with
Here.
We can make you, send it to.
I think I have the connection now, I just need to. Screen.
Your W. Yeah.
Can you pull this one? So you see the, yeah. Okay, so were people able to open it on their own laptop and, yeah? Okay, so how do we model a hadronic resonance? So this is a bit of an exercise in how this complex function works. So M is the free parameter in the model that as we move the mass of our observation around, we're gonna get different complex values for this quantity. And so we can think of what are we gonna measure experimentally? Experimentally, we measure the mod squared of this amplitude. So we think of measuring this intensity, I, as a function of mass. That's what I was showing you in that histogram that we saw of the spectrum from the Bell collaboration. But we can also measure the phase. And so this will be an important aspect of looking at interferences between different quantum mechanical amplitudes. So you can run the bits of this Python workbook in VS Code or wherever you prefer. And we define this Bright-Wigner function that just returns the thing that was written in that previous equation. And we can choose some parameters. So you can pick what the mass and width of this guy is, and you can assign those. And then when you plot the intensity, you'll get different shapes for this Bright-Wigner intensity depending on what you pick. And so, play around with that, try different masses and widths and see how it affects the intensity distribution. But imagine in parallel to this, the curve that's here, some experimental is telling you that there are data points that are along this curve, and you could fit that model to your data. So you could vary the width or vary the pole position, the mass centroid, the M0 value, until it lines up with your experimental measurements. Now, this is the case if you have a very simple, just one resonance contributing to your spectrum. So that's like the kind of simple picture we saw from the Bell collaboration. But I also showed you versions where there are overlapping resonances that are next to each other. And it turns out those give us much more complicated and interesting distributions. So yeah, you can look at and spend a couple minutes trying different things out in this exercise. What happens if you change this M0 or if you change gamma, the width, and how it modifies the distribution? I told you also that this phase is important. So it turns out that this phase motion is something that's unique to a resonance. The Bright-Wigner has an expectation that you go from basically 0 to pi as you cross the resonance. And so if we have a real quantum mechanical feature in the spectrum, we should have this complex phase parameter varying as a function of mass and having a maximum change or maximum slope right at the peak of the resonance. So when we look at some plots a little later today, we're going to be looking at phase motion and also the so-called argon diagrams that tell us about how these things describe resonances. So the other way to look at this is the argon diagram, which plots the imaginary part of this amplitude. So this Breit-Wigner function A, the imaginary part versus the real part, and it makes this circle in the argon plot. If you just have one of these Breit-Wigners that's there. Okay, people would execute that and see similar plots in their code. All right, so this looks kind of trivial. If you just have one Breit-Wigner, it should just make this simple path around here where the phase motion that going from 0 to pi is encompassed by going around this circle. What happens if we don't just have one resonance, but we have a couple of them? It starts to get a little more interesting. So let's skip this one for time, this production phase. It turns out you can choose this phase parameter a little differently, and you get a slightly shifted argon diagram. So you can basically choose whether you want to have the thing, the bottom of the circle oriented at 0 and directly up here, or it's rotated by this pi over 4. But more interestingly, and what happens much more commonly in our experiments, is we have two of these Breit-Wigner amplitudes. So at the quantum mechanical level, there's really two resonances that are contributing. There's A1 and A2, let's say, and we don't know which one is which yet or what they're describing. But when we take the square of that, we have to add those two complex value functions together and square it. And so we get what looks like two individual terms for the contributions for particle 1 and particle 2, and also this interference term, which is A1, A star. And so what we're going to measure is the sum of all three of these pieces. But the things that have only to do with particle 1 are in this A1 squared, and only to the particle 2 are A2 squared. And so we need to include this more complex model to describe our data or to fit our data. And so the picture looks like this one, that the coherent sum of those two contributions is in blue, but the individual contributions for, say, a resonance that had a mass of 0.95 and another one that had a mass of 1.1, those are in these separate curves for green and red. But the combined effect in total is really this blue one that has to do with both their individual contributions and the interference between them. And it turns out that this interference is the primary way we see lots of the rare signals in the experiment. That we have some really strong resonance, and there happens to be another one nearby, and the interference between those two is the primary thing that we see experimentally. Okay? So you're going to see in plots later curves like this one where there's some total histogram that looks like the blue thing, and we're fitting it with a model that has these complex valued functions that are trying to describe the individual components of the quantum mechanical system. Okay, so I'm going to stop there and ask if there are questions or people want to talk about the exercises here. No questions? Okay, there are a couple of extensions here you might try in your spare time, and especially when we try to, we're going to look at some data in a minute, you might try to modify the parameters of this model to match something like what looks like in the experimental data that we'll look at from various experiments. Okay, so I'll stop there. Do you want me to just share my slides from here too? That might be easier than coming back. Okay, so you can share the slides. Okay, so the other aspect I mentioned, The other aspect we were talking about a little bit before the break is that this width is really what happens in the in physical sense without any detector. So these things are broad, not just because there's some detector that measures them poorly, but their nature has this width given by their lifetime. So sometimes we have to figure out how to separate that width from the detector resolution, the smearing that we get from our detectors not being perfectly idealized. And that's for this Voisin model. Okay, so that's how we look at resonances, and we'll try to look at those in some data in a minute. But imagine taking that Breit-Wigner function and trying to fit these black data points as a way of measuring the mass and width of the state. Yeah, question.
So wait for the microphone or just go.
We can wait for the microphone. I'll take me for here.
So I have a very naive question regarding the separation of the signal from the resolution of the detector. There is this, has there been a measurement or a test of, for instance, using unfolding for separating the two things and then do a fit that does not include the contribution of the resolution of the detector?
Yeah, good question. So there is the possibility to do something called unfolding, where you have both a model of what the detector response looks like and a model of what the generated events look like in your simulation. And there you can take out these detector effects through a process called unfolding. The same thing can be done here, but unfolding typically requires a multi-dimensional distribution. So if you want to deal with multiple dimensions like fitting angles as well as masses, then you would need that. If all you care about is this one-dimensional function, then you can just use a Voisin, which effectively is an unfolding of the resolution of the detector and the natural width of the particle. But in a higher dimensional space, unfolding becomes much more useful. I'm not aware of examples where it's used commonly in spectroscopy, but it is a technique that could be applied. Yeah.
Thank you.
Yeah, good question. Other questions? Okay, then let's look at some data. What has been observed in the state of so-called charmonium? Almost 50 years ago, or a little more than 50 years ago now, there were two experiments that were trying to look at things that were heavier than what had been observed in the up, down, and strange quark sector. One of them was happening at Brookhaven National Lab. It was a proton beam hitting a beryllium target, and they were looking at electron positrons that were produced there. Another one was happening at SLAC. This is a lab in California where they were looking at electron positron annihilation. Two experiments are happening at the same time, two separate collaborations. It occurred in 1974. This is what's known as the November Revolution, where around the same time they both agreed to release their results. Unfortunately, they gave them two different names. The group at Brookhaven called it the J particle, continuing after the kaons. They went up to J. And the group at SLAC called it the psi meson. And so forever since, we have known this particle as the J psi. And so this is the lightest charmonium state. It's a charm anti-charm system, just like the phi meson is a strange anti-strange system in the light quark sector. And this really revolutionized the field of hadron spectroscopy because we knew we had a whole new flavor of quarks to deal with. And so we've measured essentially something like this measurement of this sharp enhancement in the cross section of measuring electrons and positrons annihilating. You can measure the same thing, but just going to higher masses above this 3.1 GeV where the J psi exists. And you can see all kinds of interesting structure. So this is that same measurement effectively. It's the ratio of electron-positron annihilation to quarks and antiquarks, so hadrons being produced up here, over the electromagnetic background, if you want, producing a muon pair. And if you measure that ratio, you see big spikes every place that there are hadrons. There are anti-charm systems that are produced. So the J psi, this lowest mass charmonium, is way off scale. It's orders of magnitude higher. There's another one called the psi prime. That's an excited version of the same anti-charm system. And then there are a bunch of these other bumps that appear in the spectrum. This is potentially all kinds of additional hadrons that are still anti-charm mesons that exist, and they get different mass values assigned to the higher mass states. So in terms of, we're going to be looking at plots like this quite often today, where we're going to plot the mass of some observed particles or predicted particles on one axis and the quantum numbers on the other axis. And so all of these J psi or psi mesons live in this column, the 1 minus minus column. So those are the vector mesons. Why do we know that these things produced in E plus E minus annihilation are vector mesons? Why do we know that they have quantum numbers 1 minus minus? Anybody have any ideas? What gets produced in the intermediate state between when you collide an electron-positron and the final state hadrons?
Yeah, photon. Yes.
Photon. Yeah. So when you collide electron-positron, you produce photons. The quantum numbers of that system are photons and only photon-like quantum numbers. So we must produce only vector mesons in this 1 minus minus column. Okay. It turns out later we observed lots of other charmonium systems that don't lie here, but that's where the primary action was early on, was looking at these 1 minus minus systems. Okay, so we only make those in E plus E minus. Now, here's where the spectroscopy picture kind of comes in. It turns out that if you go look at other systems that are made up of charm and anti-charm, you can watch them decay. And most of the time, they're going to decay by emitting a photon and decaying to a ground state charmonium system. So this is a bit of the analogy between the conventional spectroscopy, and we'll look at a comparison to the hydrogen atom in a minute. But if you produce lots of anti-charm systems, you get peaks in the photon energy that's emitted when one of these anti-charm mesons, called the psi 2s, decays to a photon plus something else. And you can basically ask, what is the mass of something else, given that this thing has a fixed mass and it emits a photon at a certain energy? These peaks are associated with individual particles. So they go by the name of the chi-c states. And you can look at sort of the decay diagram over here. If you start with a psi 2s, there are lots of ways for it to emit a photon, decay to some other particle, and then result in the ground state J psi. Okay, so the J psi is the baseline ground state energy level. Think of all these things as excited states of the charm system that decay by just emitting photons. What's the analogy to the hydrogen atom? Well, think of those excited states of the hydrogen atom, and they emit photons. And if you measure those photon lines, say the Balmer series in the visible spectrum, you get fixed monochromatic energies of the emitted photons from the hydrogen atom. It's the exact same thing. Over here, we just have excited states in the hadron spectrum rather than excited states in the hydrogen atom. Okay. So this was a really nice connection between the strong force and the electromagnetic force, that we could look at these simple states, if you want, of charm, anti-charm, and describe them by just having regular conventional quantum numbers. They're all predicted, they're all allowed JPCs for a charm, anti-charm system. So these are these other allowed JPCs over here. And they can be described by this simple picture of just a quark anti-quark system and emissions of photons that allow us to go from excited states to the ground state. Okay. So this was, let's say, late 80s, early 90s. We thought we understood this charm, anti-charm system really well. we could think of it in terms of these conventional quark anti-quark systems. So everything's good so far. And then people extended this to the bottomonium sector. So you can look at a similar reaction of electron annihilation at higher energies. Now this is up to 10 GeV at the Bell experiment that we looked at earlier in Japan. And they see these bumps as well that they associate with the so-called upsilon meson. So this is like the J psi, but it has a bottom anti-bottom. And you can look at all the kinds of electromagnetic transitions, and they appear at the expected masses as well. So far, bottom and charm mesons look like they match our quark anti-quark picture. But I probably wouldn't be up here telling you about them today if there wasn't something more interesting. And that's where these supernumerary X and Y and Z states start to show up. And they're hypothesized to be states that don't fit into this conventional quark anti-quark picture. So what evidence do we have for them? That's what I want to walk you through in the next several minutes. So this is that picture again from the Bell experiment. There they collide electron positrons and make bottom anti-bottom systems prolifically. And one of the ways that the bottom anti-bottom system is produced and then decays is with this B meson. So the B meson is a anti-bottom up quark, and it can decay into a system that has a psi, a charm anti-charm, and a kaon. So this goes through some standard model interactions that I don't have time to tell you about. But you can make a J psi a psi and a kaon. And so what people looked at was this X that was produced with 2 pions and a J psi, so it had to have charm anti-charm in it. But it wasn't expected. If you look at the spectrum of the predicted and discovered mesons, you get all these ones we were talking about before that were in yellow. So that's the psi 2s, the charm anti-charm, and all of these other excited versions of the same thing. But then above that, there are a bunch that are predicted that we haven't seen yet. Those are in gray. And all the ones in red are things that have been observed, but were not predicted by this conventional charm anti-charm picture. And so I'm going to walk you through a couple of examples and then tell you why we think these things are interesting. Yeah. So this is where we see this big peak. This is 2003, the first so-called XYZ observation. And for the last 20 years, we've been plugging away at trying to find more of these exotic kinds of candidates. The interesting thing about this one is actually its mass and its width. So it sits here at 3.87 GeV. It gets the name 3872 because that was the M0, the mass position value of the peak that was first observed. And we didn't know what it was, and it didn't fit into the picture because it lies up here somewhere, 3872, and it didn't match with the mass and width predicted by these models that described everything down here in the lower mass range. So what's interesting about it is that right here at about 3.75 GeV is where you can produce 2 open charm mesons, the D mesons. And it turns out all the interesting stuff starts to happen above that range. So we can describe all this really well in terms of the quark model. Once we get up here, things get quite interesting. So we call this thing an X because we don't know what it is, and it goes by this name. We're going to talk more about other particles called Y. They're also things we don't know what they are, but they have a particular set of quantum numbers. They're the 1-minus states that we make in E plus E minus annihilation. And everything that gets a name Z is going to be electrically charged. And that will give us more information about what the quark content can be. So how many are there and how interesting are these things? Well, this is a review article from already almost 10 years ago, and it has that same picture of the transitions of how these particles can decay from one to another. So think of each one of these lines as a way that a particle can, like in the hydrogen atom, emit a photon or emit an ion and decay from one to another. It's a zoo. There's more of them than we know how to describe. The pictures are not quite clear, but there's definitely interesting stuff going on here because there are new resonances that we didn't know about just 20 years ago. Right? So what I'd like to try to walk through is a couple of examples of these and why we think they're interesting, and then I'll pause along the way and let you ask questions. So this X3872 is one that's better known than many of the others, and that's because it comes in the production and decay to lots of different channels that we'll look at in a minute. Okay, so everything started with this X3872. What are the possible interpretations for how it can be manifest? So it could be that our model for the charm-anti-charm systems, these conventional quark model things, is just wrong. Maybe we got it wrong, and even though we described everything in the low mass region, the model just isn't able to describe the higher mass state. However, there are other more interesting connections, and one of them is that it could look more like a hadronic molecule than a conventional quark-anti-quark system. So this is a bit of a fuzzy interpretation, but basically it's talking about distance scales. So you think about a quark-anti-quark system, that's a confined state of two quarks. That's a very compact, small size object. If it were more like a hadronic molecule, which is a couple of separate hadrons that are sort of orbiting around each other, both spatially, but not at that compact spatial size, then it would look more like this hadronic molecular picture. And then there are ideas that it could be a tightly packed tetraquark, so these 4 quarks on top of each other. Now, why do we know that it should have 4 quarks inside of it? Well, it has this charm-anti-charm. So if it's going to have charm-anti-charm and something else, that means it needs to have more than 2 quarks. And so that's what makes it a possible tetraquark candidate. So I'm going to try to show you a couple of examples of data where people have made more measurements of this state to try to tell us something about its nature. And some of it is how it behaves when it's around other matter. So back to our question about how we can categorize these kinds of hadrons. Well, one of the ways we talked about doing that is by looking at the quantum numbers of the system. So we came up with a list of all the possible quantum numbers over here. You might start by asking, does this big peak in the spectrum have exotic quantum numbers? Is it a candidate for one of these exotic mesons? And this is an example of how you would try to determine that. So you can look at the data that's in black points. It's the same in each of the plots. And you can compare that to a model of what if the hypothesized particle, or what we observe here as a peak, was this particular quantum number, this is what the model would describe it as. And so any place where you see disagreement with the model is telling you that that's not a good model to describe the data. So these quite high spin, like J of 4, obviously peak at these large angles of decay of the particles. And that doesn't match what we see in the experiment. So we can rule those out. It can't be a spin 2 or 3 or 4 system. If it was a spin 0 system, it would look pretty flat in these angles. So it wouldn't have much angular distribution. And so those get ruled out. And the 2 most likely ones that are consistent with the data are these spin 1, 1 minus plus. That would be an exotic. And this one would be a conventional quantum number system. And it turns out that this one is preferred with some number of sigma of accuracy. And this is an earlier publication. This has been superseded later. But we know pretty well that this is a 1++ quantum number. So it's not exotic, but we can classify it as being a new charmonium system to look at. The other thing we can look at is what is the mass of the system. And the LHCb experiment that produces more of these B hadrons than anybody else in the world has measured many thousands of them, more than just this is maybe 50 events total. So it's a really rare signal. At LHCb, they're measuring thousands of them now. And so they can measure this mass more effectively. And there they can place it on this table of mass versus quantum number. So we've got it in the 1++ column, and we know its mass pretty well. And it doesn't line up with any of the predicted quantum or predicted masses from the conventional Charmonian picture. So one other thing you can do is try to produce this system other ways, or you can look at how it interacts with matter and try to say something about it. And so what the LHCb experiment did was look at how this X3872 decayed to J psi pi pi relative to well-known system called the psi 2s. So this is a conventional Charmonium system. This is the maybe interesting one. And you can see it's changed its name here. It's now known as the Chi C1 because we think we know more about it than we did when it was originally observed. And you can look at how it decays. This 3872 is produced in decays relative to the psi 2s. And you can measure that as a function of how many other tracks or how many other particles are produced in the collision at LHCb. So remember, we're colliding proton proton. We produce this X3872 plus a bunch of other stuff. And if in the midst of all that other stuff, you produce more of these guys than at low multiplicity or low numbers of tracks, then you may be more consistent with a tetraquark or a molecular kind of model. So these are model curves here. Whereas at the higher multiplicity, when you produce a lot more other stuff in the reaction, then you get a different model expectation for what the variation of this ratio should look like. And so the verdict is really still out here. We think it's probably some compact tetraquark and maybe even a mixture of this molecular kind of object. But there are more measurements going on at the LHC and potentials to look for something like this at JLab, but we need more energy. And so this 12 GeV electron beam doesn't provide us with the coverage to go and look for these excited states. And that might be something we could do in the future at JLab or at the electron ion collider, where they will have plenty of energy to produce these kinds of exotic states. Another thing you can do is look at how these things travel through medium. So we do lots of things here at JLab where we use a proton target and a deuterium target and a helium target and a carbon target and look at how the modification of how particles travel through nuclear materials happen. You can do a similar thing at a place like the LHC, but instead of having a target made of lead, you collide two lead ions and you produce a quark gluon plasma, all kinds of quarks and gluons floating around. And you can basically ask, how often does a particle like this X3872 make it through a system like that? And what they observed is that the X3872 is much more likely to be produced and make it through the system in a lead-lead collision than in a proton-proton collision. So how can that make sense? It could be possible that most of these hadrons are really being produced as they travel through the medium. So going through the medium, they somehow coalesce because you have lots of quarks and gluons floating around, and you could make these kinds of molecular systems easier that way. So there are more probes to look at if we can look at it in different production and decay mechanisms. And I'll maybe skip this one and talk about what you could do at the EIC. This is a bit of a picture of what this might look like. At the EIC, you have an electron beam. And so the electron beam comes in, you could make something like this X3872 inside of a nucleus. You had an ion beam to hit with your electron. And then you could basically ask, how easily does it escape based on what the A of the nucleus is. And so you can imagine doing experiments at the EIC where if it's a compact object, it would basically not depend on how thick the nucleus is that it has to travel through. Whereas if it was a molecular kind of system, you would get some fall off as you went to higher A in the nucleus as it had to travel through more material. So there are ways we can try to probe these in a little more detail, but the short answer is we don't really know exactly what the properties of this X3872 are yet, but we're working on it. So maybe I'll pause there and see if there are questions about this one before I talk about some more examples. Any questions about X 3872? Okay, we can come back with more questions. So what are some other cases and how am I doing on time? 15 more minutes?
Yeah, 15, 20.
Okay. So another example is the so-called Y4260. It's called Y. Why is it called Y? Because it's a vector quantum number, the 1 minus minus. So you can make it directly in electron-positron annihilation. So in that electron-positron annihilation, turns out you can emit photons in the initial state to give you the right mass to produce the state Y. And around the same time in the early 2000s, we saw this feature in the spectrum. It's been measured much more precisely than that more recently. Actually, turns out there's 2 peaks buried inside of there. And this is what you find as you do more and more of these spectroscopy measurements. The closer you look, the more interesting or maybe the more challenging it is to interpret what's going on there. So there's a whole mess of Ys that apparently live at the higher masses of this this column, the 1 minus minus. So how do we interpret them? Well, we can look how they decay. And it turns out some of them decay in a very interesting way. So this is the mass of the J psi pi pi. So it's that same mass spectrum we saw the Y4260 in. But we're looking at higher masses and a different production mechanism, electron-positron annihilation. And if you look at how that particle decays, if you keep those events in that peak, and you look at just one of the pions with the J psi, you see this huge peak that we call the Z sub C. Why is this one called the Z sub C? Well, it is charged. It must be charged because it decays to a J psi, so it has to have charm anti-charm. But charm anti-charm doesn't have any charge. It's charge 0. And so you've got to have more quarks inside of there to give it charge. So what is the interpretation of this Z sub C? It's got to be charm anti-charm because we see it decay to J psi. And it has to have 2 light quarks inside of it that give it the charge. In this case, a pion for the charged pion. And so this thing has to have 4 quark content. Now, does it have to be a tetraquark, this tightly bound system of 4 quarks? Not necessarily. It could be more like a molecular kind of system, but it definitely has to have 4 quarks in its nature to be able to decay this way. Right? So there's been more measurements here. Again, the verdict is still out a little bit, but this is another interesting candidate. Maybe I'll go briefly over this one so we can get to the pentaquark stuff. It turns out there are other Z's that are measured. This is another measurement from LHCb. They can do an analysis where they find that there's a Z4430. Note that this is about 500 MeV heavier than this Z3900. It turns out that 2 experiments don't see the same spectrum of Z's. So one sees a particular set of Z's, the other one sees another set. And so there's not quite a coherent story between the kinds of observations we see at the different experiments. Now, they're different production mechanisms, so they could just produce different sets of hadrons, but we don't have a coherent picture that describes all of them together. So the short summary on these heavy quark meson states, the so-called XYZ systems, is that we're making them and they're getting made more and more, or observed more and more with new experiments. There's not necessarily a coherent understanding, but there are these ideas about describing them in terms of both the tetraquark kind of 4 quark objects as well as molecular systems. The molecular systems are a little less exotic because they can be described in terms of just hadronic degrees of freedom. But the tetraquark systems would be really a unique feature of QCD that we could try to unravel by digging into them more. All right. I want to spend the last few minutes talking about this object called the pentaquark. So who's heard of the pentaquark before? Okay. There are a couple different kinds of pentaquarks. One was there was an original observation. People thought they saw a pentaquark at JLab. This was before I got here 20 years ago or something. That one has been disproved. But recently, meaning in 2015, the LHCb experiment observed a new charm pentaquark, which was kind of part of this revolution of the exotic charmonium systems. So how do you produce a pentaquark at the LHC? Well, you collide two protons together and you make one of these heavy lambda B baryons. So this is an up and a down and a bottom quark. So it's quite heavy. And you can watch it decay. And often it decays to J psi proton and a kaon through a Feynman diagram like this one. And so you can look at systems like, what if it makes a J psi and a lambda star, where that lambda star decays to K proton, and you get a really broad and messy mix of states in the spectrum. So you see all these peaks and features, those are all different excited states of the lambda hyperon that are down here. So these are things we think we know well from other measurements at JLab and other places about the spectrum of lambdas. And you can see these broad and overlapping things. Imagine all of those as one of these complex Breit-Wigner functions that's describing the contribution to this mass spectrum. The data is in black. And what you see on the other panel is, what if instead of looking at the K proton mass, looked at the mass of the J psi in the proton? So over here, you also see these sharp features, and none of them are really described by this lambda contribution from diagrams like this one. They look like there must be a peak here that is something like this diagram, where you've got a kaon that's kind of the spectator in the system. And then you've got this 5 quark object that has to have the charm anti-charm for the J psi and the up, up, down for the proton. And so because it has charm anti-charm and it has charge, this 5 quark description is what allows us to describe big peaks in the spectrum like this one. So this blue thing here and this broad magenta are the so-called P sub C pentaquarks that were observed by LHCb. This was in 2015. In 2019, they measured it even more closely, and they found that there were really 3 features that were needed to describe the shapes that they see in the mass spectrum. So again, as you zoom in, as you have more data, we learn there's more complexity on the features that we see in the data. But let's go back to our picture of the argon plot for these Breit-Wigners we were looking at before. So in your Google Colab notebook, you were plotting things like the intensity as a function of mass with that M0 and lambda value, and looking at this phase variation, which would give you a circle diagram. This is an example from data where they measured at various points along the mass spectrum what the imaginary and real part of that amplitude was. And they see that it had this circular kind of shape in the complex plane. So this is an indication that this thing is a real resonant structure coming from this Breit-Wigner-like description of its line shape. So what can we say about these new features in the spectrum? Well, quite interestingly, they start to show up where new thresholds open. So there are open charm systems, the D meson and the sigma C baryon, which can only be produced starting at exactly this mass where the dotted line is, or an excited version of the D star 0, which have a threshold that turns on right here. So quite interestingly, a lot of these features in the charmonium systems appear at places close to where those thresholds show up. So why would a new threshold opening give us an enhancement or an intensity increase in that region of matrix? Well, diagrams like this one have been hypothesized to be a potential source for that. So if you have the lambda B that decays instead of going to a pentaquark and a kaon, what if instead it went to an excited lambda and a chi sub C, and then that lambda decayed to proton K minus, and there was a rescattering. So down here, the proton that was emitted from this decay interacted with one of the elements of the decay of the lambda B originally, and that thing could rescatter down here. So that rescattering could give you a peak, basically in the mass of this proton J psi associated with that, the place where that rescattering occurs. And it has to do with what the masses of the elements of this loop are. And so there are ideas that can describe the data with near these thresholds in terms of some of these rescattering effects. So these are ways we can try to probe if these are really new, unique features in the data that have to be due to resonances. They are definitely in the data, but could they also be described as other kinds of contributions that aren't this tightly bound pentaquark kind of a model? The answer is briefly yes. And there are other ways we could try to produce these things and study them. So when this was observed that in J psi proton, you saw these structures, people at Jefferson Lab said, well, hey, we make J psi proton. Why can't we look for these kinds of structures in our data? And in fact, we can. With a photon beam and a proton target like we have at GlueX, you can think of the photon being sort of like a virtual J psi and scattering off the proton. And if you have that, you can produce in the S channel these same pentaquark type objects. So if they're really there in their resonances, if the coupling is strong enough, we should be able to see them in our data. And you would see them as a peak in the S, the center of mass energy of our collision we were talking about earlier. And they would appear as peaks in the spectrum, as the cross-section of producing J psi proton as a function of beam energy. And it turns out up to 12 GeV is exactly the place in energy where you would expect these kinds of features to show up in the data. We measured that at GlueX. There were other experiments at JLab that have measured similar things. Turns out we don't see any of those features in the data at Jefferson Lab. And so we can set limits on the coupling, how often, if we're producing pentaquarks, they should decay to J psi proton. And it turns out they're at the couple of % level. There's another plot here from one of the other experiments in Hall C that's even planning to run an extension of this experiment coming up, where they measure things, the contributions down to like sub % levels for the branching ratios. So the short answer is, if we are producing pentaquarks like this at JLab, the coupling is so small that we can't see them, and it's tough to make that reconcile with the way they were observed at LHCb. Yeah, I'll skip over that. This one is talking a little bit more about these rescattering diagrams. If you want to know more about it, I can come back to that one. But I'll briefly just mention there's lots of other ways or places to look for these kinds of maybe conventional hadrons. At LHCb, they're also producing prolific numbers of charm strange systems, so-called omega C baryons. They make doubly strange or doubly charm baryons. And even looking at the omega sub S, 3 strange quarks. This is at Bell and also at LHCb, looking at strange and bottomonium systems as well. So there's lots of exciting stuff going on in spectroscopy. And today I wanted to get to all of that heavy quark stuff so that we could focus on the light quark things tomorrow. But the short answer is there's really quite a spectrum of conventional charmonium bottomonium systems we can measure really well, and we think we understand. But there's been an explosion of these new XYZ states. And we're looking, as I mentioned, for the patterns in the spectrum that we. So far, there are some models that can describe some of the observations, but there's not a coherent model that can describe everything. And so that's one of the things that we're after with measuring these with higher precision and really trying to convince the theoretical community to come with a sort of complete model that can describe that data. And there's lots of interesting stuff going on in these pentaquarks. We don't see them at JLab, which is surprising, maybe, if they're really hadrons that should be produced everywhere. And so we're really at a sort of a turning point in the field to try to describe all of these observations in a coherent way across experiments, which is what we're after right now. So I'll stop there and take questions.
Has no one observed any top quark baryons yet?
Yeah, so the top quark is so heavy that it turns out it decays before it can hadronize. And so it's above the mass of the W boson and the Z boson. And so there are decays through weak interactions that cause us to not be able to effectively make hadrons out of top quarks. So unfortunately, no higher mass scale to go searching for these things. We're stuck with charm and bottom.
Oh, well.
I was curious, so on slide 67, you were talking about like measuring that argon diagram.
Yeah.
How do you measure the imaginary and the real components of the asymmetry data?
Yeah, good question. So effectively what you can do, and we're going to talk a little bit more about this tomorrow, is that right now, the curve that's shown here is this model of the intensity as a function of mass. So that's the I as a function of M that's in your Google Colab workbook. You can, instead of providing a functional form for that, just say, let me put 3 parameters for the real and imaginary parts of that model at this point, and at this point, and at that point, and at that point. And you can extract those 2 components separately. And that's effectively what's done over here. Is you put in, if you want a piecewise function for the model for, this one was the 4450, so it's this blue thing. And they say at a few specific points, ignore a mass-dependent model, but just put in 2 real numbers, the real and imaginary components at each one of those points, and then measure how that changes as a function of mass. And then you can measure those points along the way. We call that the so-called mass-independent analysis, that we're really trying to not assume a model for the mass dependence, but extract the mass dependence of a particular tooth. Yeah.
I guess I have a follow-up question to that one. So let's say we're fitting our data to like a Voisin instead of just like a pure Brett-Wigner.
Yeah.
How does that affect, like, can you still make like an argon diagram like this, like a mass independent analysis? And if so, like, how does it affect the I don't know, like the shape of it, I guess?
Yeah, okay. So good question. So in blue here, we have what is a combined, if there's both detector resolution and the width of the particle, both of them are built into the model that's shown here. I think what you're asking is, if we didn't build in, if we had sort of mass independent bins, how would we build in the mass resolution? I guess is one way of thinking about it. The short answer to that is almost always the bins are wider than the resolution of the experiment. So as long as your bin, so if you're building up a histogram, the histogram of my mass has 20 MeV wide bins. And my mass resolution was only 5 MeV. Then if I measure here, or I measure here, or I measure there, it's all measuring pretty much the same thing because I'm smearing out my data across the bin. But if my bins were much narrower than the mass resolution, I'd have to deal with this extra factor. So most of the time, we just bin it such that we don't have to deal with the mass resolution.
Gotcha.
If you did, you'd have to have a convolution of this resolution with the model inside of that bin. And that would be, complicated. Possible, but complicated. It might go back to this unfolding idea. You would need some more information about the generated signal Monte Carlo and the data in that bin. Good questions.
So my question is related to the slide in which you mentioned the EIC. I'm kind of curious about what would be maybe like the production mechanism of the X in this environment, because so these complex structures, it makes kind of sense to consider them into a coalescence model or a high multiplicity environment. But in this case, there is an electron that goes, interacts with nuclei. Maybe it breaks it, maybe it not. So what could be like a production mechanism in here?
I think I may have a backup slide. Let's see. Nope. Okay. Then we're going to talk more about this tomorrow. But in these, in this kind of a picture, we're thinking of the traditional photo production mechanism, which goes through a T-channel diagram. So there are a couple ways to do it. You can have a photon come in and hit one of the nucleons or a nucleus in the target. You want to produce an X, so you need to exchange some hadron here, and so there's going to be some a pion or a rho or something else that you can think of as being emitted from the nuclear target, and that interaction causes you to make the X.
So this would be a kind of elastic event?
It can be elastic, but you could also break up the nucleus. So there's nothing requiring exclusivity necessarily in the interaction.
All right. So then it's basically this is mediated by this kind of virtual meson exchange.
That's right. So we have some kind of hadronic exchange. And that goes by the name of Reggie theory. So there's a whole set of phenomenology that allows us to describe the production, peripheral production, if you want, where we have some exchange, virtual exchange hadron, or things that have hadronic quantum numbers that produce the state X. There's another interesting possibility. It turns out that when you have these atomic nuclei that are there as a target or as a beam, there are photons nearby, virtual photons. And you can go through what's known as the Primakov process to actually emit a photon from the nucleus. And in that case, you can actually have photon-photon interactions. So what if instead of having a hadron exchange, the nucleus has this sort of virtual cloud of photons around it? What if you emit a photon? So you really get a gamma-gamma interaction that makes X. And that's a possibility as well. This one goes by the name of the Primakov process. And we use it in real photon beam experiments as well to try to look at gamma-gamma kinds of interactions. Not often for spectroscopy, but it can be used that way. So there are different production mechanisms. We have to rely on our theory colleagues to come up with good models for how this could happen. It does depend on the knowledge of how this X couples to these kinds of interactions, which is a bit unknown. I mean, we know how the X decays, but we don't know a lot about how it's produced. And so there can be big uncertainties in the kinds of models we come up with.
So I have a quick question. So when fitting the J-psi peak, so we know the natural shape of the J-psi peak is Breit-Wingler, right?
Let me go back to the flower. You're thinking about this mass spectrum, the J-psi proton?
No, just the J-psi peak.
Oh, just the J-psi.
So does it have the natural shape of the Breit-Wingler?
The J-psi does, yes. It has the natural shape of the Breit-Wigner, but it turns out that most of the detectors that measure it have much bigger resolution, much worse resolutions than the natural width. And so when you measure the J-psi, you're dominated by those detector resolutions rather than the intrinsic nature.
So does it depend on the decay channel? So we know that J-psi decay into two leptonic decay channels, right? E plus, E minus, and mu plus, mu minus. So in both cases, does it have this same shape?
Yeah, it's a really good question. And let me go back to that. So the thing that tells you about the natural width of the particle, if you had a perfect detector, how it was going to be measured is this lambda total. And so that is the thing that governs the line shape that you would see experimentally if you had a perfect detector. And that is independent of the decay mode. So that's the same for any J-psi decay mode that you would want to look at. So whether you're looking at electron positron or V plus V minus for the J-psi decay, that natural width will be the same. The detector may have very different resolutions for how you measure it. So you may measure electrons better than muons, and you have different widths that you measure experimentally. But that natural lambda total is the same for both. You will list the lifetime of the part.
One question about the pentacoax, like since the decay is very fast, right? The decay time. Interpret that in case of pentacoax. The decay rate is very fast.
Decay that is very fast. Yeah, so all of these productions and decays are happening at timescales where we can't measure, let's say it this way, when the pentaquark decays to J-psi proton, it's happening before we could ever measure that it lived for a finite amount of time. Our detectors will never measure the femtometer type distance scales it travels before it decays. So can you say the question again then?
Is it like, or my question is like, if the signal is whether, how we can interpret whether it is a random fluctuation or a signal?
Okay. So whether we determine it's a random fluctuation or a real signal is really governed by this intensity distribution. So when we talk about how significant a signal is, we say, here is the data we measure, which is just the number of observations we make as a function of mass. So forget about the models, the curves, they don't exist, just data points with errors. That's just how many we measure at in each one of these mass bands. And that's integrated over data that was collected over years. So we collect a big data set and we measure this histogram. What we then ask is how likely it is that data could be described by the background only, this black curve, compared to what the red signal looks like, we call this hypothesis testing. So you compare your model that has a signal in it compared to a background only hypothesis. So compare the red and the black, and the comparison of those two, you can come up with a probability, a p-value for how likely it is that it could just be a random fluctuation compared to the background. And we call that the number of sigma for the observation, or the significance of the observation. And these are way above any statistical measure that would be required for an observation. So something is definitely there, but what it is, the interpretation of it is harder to say.
The error was also like statistical errors.
That's right. So these are statistical errors, often also convoluted with systematic errors. It turns out these are mostly dominated by the statistical uncertainty rather than systematic variations.
Thank you.
Any other questions?
Is there any like suggested value for the experimental community to determine up to which value of sigma we should consider? Or it to consider a peak, not a fluctuation?
Yeah, good question. Depends on what field you're in. So in the medical community and other places, if you have better than or more than a 5% chance that it would a p-value of 0.05, that it's not a statistical anomaly, they would call that a significant observation. So if it is just 5% of the time it was random chance, they would publish that and say this is meaningful evidence. We're a lot more strict in the particle physics community. Typically, we require for a real discovery a 5 sigma effect. And if you look at what fraction of the time that you could randomly get that answer from a statistical distribution, it's something like 1 in 10 million, I think. So it's a real, if we measure something at 5 sigma, it is deal. It has to be there. But we often, in a paper, will talk about things like an observation, which comes with like a 4 sigma kind of significance, and even things that have 3 sigma, which is already like a 1 in 10,000 kind of a probability. People put in papers as maybe very strong hints that something could be there. So it depends a little on what field you're in, but anything less than 3 sigma, forget about it. It's probably just noise. When you get above 3 sigma, people get interested, and by the time you get to 5, it's definitely something there. Publications with 3 sigma claims of significance have been shown to be wrong later. There's yeah, some history of these kinds of effects.
Okay, let's stop here.